Okay. So today I'm going to speak about Koopman-driven grip force prediction through EMG sensing. So I apologize to those who were in Denver because this is basically a very similar talk, but the second part will be more interesting, I guess, because we will have a little demonstration here. So mainly this is the part of PhD thesis that our brilliant student Tomislav Bazina did and defended recently. So, okay, can you click because it doesn't? Okay. Yeah, so this is a project team. So as I said, Tomislav Bazina, who did the major work on this project, Maria Fanoberova, of course, Igor, and this is the funding for the project. Before I speak about the core topic of this talk, I'll say a little bit about rehabilitation robotics and the soft robotics. So basically, this is on a higher level what we really want to do here. So EMG and these predictions that I'll talk about are just one puzzle in this whole bigger project. I'll show experimental setup, Koopman modeling, some estimation and prediction results. But as I said, in the second part, you will also see the demonstration. So this was recently published in IEEE Transactions, Neural Systems and Rehabilitation Engineering. So if you're interested for more details, you can read it in this paper. So what really the challenge is, what we are trying to do in a high level. So there is increasing problem of hand function loss. So people have different neurological disorders such as stroke or MS. And the consequences are that those affected have problems in activities of daily living. So in numbers, 70% have limited fine hand use after stroke, for example, and then 45% of them are still affected after 18 months. So what procedures we know for now? So we have traditional procedures where you have physiotherapists, typically that work with that certain patient one-to-one. So in this case, you know that this cannot be enough frequent, so you don't have enough personnel to work with affected patients. But there is this second part, which is rehabilitation robotics, which can help overcome this kind of problems. So the key advantage is that you can enable high intensity and more frequent exercises, task-specific training. So you can have this continuous evaluation of the outcome of the rehabilitation by integrating sensors. And then typically here rigid robots are employed, but those rigid robots struggle with complex hand movements. So you know that we as humans have very complicated anatomy. So one thing that helps us here is soft robotics. So we've been working with soft robots for a while. So here basically you have structures with soft bodies which are inspired by nature. So when we started, yeah, I don't know how many years, it was 5 years ago. So we started investigating how to control those structures, which are highly nonlinear. They have a lot of degrees of freedom. So we end up publishing this in Science Robotics. And now we basically try to apply those soft robotic approaches to get something that you can see on your right-hand side. So following the soft robotic approach to develop kind of exoskeleton device which will help in the rehabilitation process. We of course started with the traditional procedures with like this traditional robot, rigid robots, but we immediately saw that this is not the best approach because you have to build a device for a certain person. Then it's not very comfortable. It limits the movement. So soft robotics always allows you this extra degrees of freedom where you have this extra compliance. So this is from Tomislav's thesis. So how we started here. So basically we started with simplified kinematics of human hand. So basically we have to simplify it as much as possible. And then we apply basically this soft robotic approach to develop structures, mechanical structures, which is basically this hand glove that you saw, that you can see on this picture. And now this upper part, this is something that I'm talking about today. So what we want to do is to kind of control these devices in a smart way. So basically, we would like to somehow measure the force that a certain person can exert, and then basically help to this person to move their hand with the force, the amount of force that's really needed. So in this case, we are using this EMG adaptive assistance that, as I said, I'll be talking about. So idea is to utilize real-time biosignals to get insight into muscle activity and patient effort. So somehow measure this muscle activity and then estimate and predict the force, the grip force of your hand. So ultimate goal would be to have this integrated device with adaptive control of this glove that you've seen. Of course, there are a lot of advantages, so you can dynamically adjust support based on patient effort, so assist as needed, amplify rather than replace neural motor commands, detecting motor intent, and thus minimize this so-called slacking effect, as they call it in the recent literature, which is often passive robotic and robots which are made which are made on the basis of traditional approaches with rigid structures. So how can you monitor this muscle activity? Basically, so you have this so-called motor units, which are a group of muscle fibers which activates via alpha motor neurons. And basically, there is a motor unit activation potential. So you can imagine it as I mean, it is voltage actually. So you measure a small voltage, which is a result of inference of firing signals from each motor unit. So we detect this basically this signals via surface electromyography sensors. There are, of course, a lot of challenges. So these signals are very low, and there is a lot of noise, and you have to deal with that. So there is a crosstalk between muscles. There is an electrode placement issue, so you never attach it to the same place. It moves a little bit. There are tissue characteristics. There are temporal and spectral characteristics. A lot of different things that you have to take into account. So what our goal and approach was that Tomislav came up with is to develop a real-time framework for first EMG signal processing, but just using one sensing position, the forearm. So there is a lot of literature where they use like whole grids of sensors, a lot of sensors, and then do basically a similar thing. But we were concentrating on getting similar results using just one sensing position, which simplifies the system drastically. So basically, we are processing EMG signal to extract features which are highly correlated with grip force. So basically, these features, you can imagine it as observables in Koopman framework, and then apply Koopman-driven estimation and short-term prediction of grip force that will later be input for the control. So experimental setup, you will see it here, so I'll go really quickly. So Shimmer 3 EMG sensors, reference dynamometer, calibrated integration is done in ROS robotic operating system. So Tomislav will show this part. We did design of experiment with two-factor RBD. So grip force levels are 100%, 75%, 50%, 25%, and 0. So we had 13 subjects, our students, volunteers who basically did measurements on 2 different sensing locations for validation of our method at the end. And this is how basically real-time batch signal processing looks. So, first, you have raw EMG signal. You basically switch to frequency domain using fast Fourier transformation. And then on such obtained signal, you apply spectral mask. So this spectral mask was previously optimized using different methods, and yeah, I'll not talk about this in detail, but we can definitely discuss. So when you apply this spectral mask, basically you keep only the frequencies that are important, and then you do inverse FFT to get back to time domain. You do rectification because you have AC signal, so it has negative values as well. So and then you do windowed exponential moving average for a little bit more smoothing, and you end up with the signal that you can see at the top. The idea would be now to estimate the signal that you see at the bottom. So you would like to estimate from the upper signal what's happening down there. So that the down signal is from the reference dynamometer. So this is the mask, basically, which was optimized on 13 subjects. Tested this mask on me later in this 13 subjects, and it worked quite well. So it basically generalizes to subjects outside of the set. And then main idea is to have personalized calibration experiments. So basically you do 30 seconds calibration experiment, and then after that you can perform batch by batch processing and estimation of current grip force. So our window was 0.5 seconds long, and the same thing for real-time prediction. So we can basically use these estimations to predict 0.5 seconds ahead. So yeah, similar as I told you before. So raw signal, you process it, and then you apply Koopman-driven estimation and prediction to end up with something that you can see on your right-hand side. So Koopman modeling, maybe I can just go very quickly through this part. So yeah, so we are dealing with observables that are real value observables. Maybe that's something just to mention here. Of course, Koopman operators is linear, even for underlying nonlinear systems. So our system indeed is nonlinear. So Tomislav did tests, and yeah. So this is maybe interesting part, because we basically apply these two concepts: static Koopman operator that Igor spoke about in his talk. So basically, both static and dynamic act on observables, but static maps observables between different spaces. So in our case, you map space of the EMG to the space of grip force, basically. And dynamic Koopman operator just advances observables in time, as usually do. And this is used for short-term predictions. So static, as I said, estimates grip force G from this processed EMG signal. And then the input and output matrices of lifted variables are expressed by this equation 3. Basically, we minimize Frobenius norm. We use SVD-based Moore pseudo-inverse. And regarding lifting, so there was a lot of experimenting here. Of course, we went with Henkel lifting, as we did similar thing in science robotics paper. So we saw that the time delay embedding works quite nice with these real systems. So we applied Henkel lifting to both E and G. Additionally, we had this concept of gridded indicator observables, which basically helped us to align EMG plateaus and transitions with grip force patterns. So as you have seen, this EMG signal is quite spiky. So this basically helped to get rid of this spike. So for each point in a subregion, which is a cube, an indicator function will assign one will assign one, and otherwise, if the point is outside of the region, it will assign 0. So grid is defined on Cartesian plane with 3 time delays, basically, and each subregion is treated as binary observable. So this way, a lot of observables are generated, but we are just keeping those who have a certain level of density. And then final estimation model. So Koopman estimation model finally is, so we have final lifted data matrices with data assembled by stacking time delayed observables, augmented with these gridded indicator observables for processed EMG, and 0 for grip force. So only indicator observables are just used in E, and then using 4 and 6, for that you've seen before, Koopman estimation model is trained on the full 30 seconds personalized experiment. So this experiment is used also for calibration and for training Koopman model. So the same experiment the same data is used for both things. So then we sequentially apply this Koopman operator to estimate basically 0.5 second batch window in real time. So that's key. Dynamic Koopman operator predicts the system evolution by mapping observables within the same space. So here we basically applied DMD methodology to first approximate the spectral properties, and then we use the method from Igor and Zlatko basically to go further. And then in this case, we again used Henkel lifting, and then we also embed this additional embedding, which is the result of logarithmic transformation of the Henkel matrix. So this was found empirically, actually. So we don't have like a theoretical background by why this worked well, but basically we experimented that it worked quite well. So then the complete lifted matrix stacked with the time delay embeddings yield a sequence of snapshots, which is here in equation 9. So after we do spectral decomposition of the Koopman operator, Koopman amplitudes are calculated. So we do least square minimization problem, and forecasting of future snapshots in horizon H is done according to this equation 11. So when we did the predictions, we also did this hyperparameters tuning. So one thing that's important in our case, so this is real application, so we want to run it in real time. So basically we would like to be as less as possible computationally expensive. So there are these certain parameters that we are trying to optimize. So number of Koopman modes, number of time delay, smooth coefficient, and this parameter which is called thinning step. So basically we are thinning the Henkel matrix. So we are doing sensitivity analysis and trying to check for how many columns we can remove to simplify the problem and still get the results at the same level. So this is just to be able to basically implement it in real time, and this window coefficient. So basically arrows indicate what were the optimal parameters, and this weighted mean absolute percentage error was used basically as a metric here. So yeah, these are some results. So on the first plot you see the raw EMG signal. So these were 3 different measurements basically, and then on this second graph you see how basically estimations look. So the measured grip force is blue, and then orange is processed EMG. So you see that there is quite nice alignment between these two signals in all 3 cases. And yeah, the red one is basically estimated grip force. So yeah, you see quite nice alignment, and the estimation weighted mean absolute percentage error was just 5.5%. So this is maybe not the lowest error in the literature. So there are some papers that achieve even lower error, but they use a lot of sensors. They use grids of sensors. So here we are at the comparable level of the error, but with very simplified experimental setup. And then predictions, of course, the error is much higher. It's at the level of 18%, but still we get some results that are quite nice and taking into account the signals that we are working with. Yeah, so we achieved this strong correlation between processed sEMG and the actual grip force. So it was at the level of 96%. We established Koopman-driven real-time framework for grip force estimation and prediction. So we estimate grip force from only measurements of the EMG signal. This was the error that you've seen. So predictions are 0.5 seconds ahead. This is processed. This is important. It's processed in only 30 milliseconds. So this is then viable to be implemented in real time. So we always have to keep in mind that this will work in real time, and everything has to be optimized for real time. And the method is robust, because we basically use only one single sEMG sensor pair, and we tried 2 different positions, and basically we got very similar results. And this is basically simplifying practical use of the methods when it comes to putting it to the patient's hands, for example. Yeah, so part 2 will basically be the demo.